All right, so our next presenter will be Mike Derivnikin. He's a graduate chemist who conducts data science analysis in the field of environmental, geochemical, biomonitoring, and arson investigation. A majority of Mike's work is done in conjunction with the environmental consulting company, Chemistry Matters, whose aim is making chemical data meaningful. Mike is especially interested in applying his background in analytical chemistry and statistics towards helping clients in their interpretation and communication of results. Let's welcome Mike.
So, although I've always wanted to become a chemist, I've had this fascination with neuroscience. There's this cool experiment in Orange University up north in Canada where they would take subjects, strap electrodes to their head, and show them various images. And kind of the goal of the study was to see which images elicit the largest electro spike. What they noticed is that images that evoked either fear or humor had the largest neural response and largest memory retention. Funny enough, these kind of techniques are what professional memorizers use. So the people who can remember to count cards, the people who remember the digits of pi, they actually make funny stories about that. So what I want to do with this presentation is have one image that's going to define the storyline of what I'm going to talk about. And this is where I'm going to engage the audience just a bit. I want everybody to look at this spinning ink blot pattern and think of the first thing that pops in their head. The more bizarre, the better. So when I see this, I kind of see a dove with a crown on its head. And if we look at this, we can kind of see the big dots are at the wings down there. We can see that there's kind of like a narrowing dot going towards the tail. And we look at the wings, they're kind of spread out just a bit more than the tail itself. What else I notice is that the small dots are in the middle of the body. And then there's kind of this triangle poking out of the middle of the body as well. And finally, the crown. Those are kind of those three-pronged Bart Simpson-like hair-like structures at the edge of this ink blot pattern. So last month I was doing a presentation and my data structure looked like Michael Jackson doing the moonwalk. That one was a lot more memorable than a dove. And it was really memorable when I tried doing my best moonwalk across the stage. Everybody remembers that one. So why do I describe data in this kind of manner? Well, this kind of boils down to what I do for a living. So when I go up to parties and I introduce myself, I usually tell people I am a forensic toxicologist. And after they're done asking me questions about CSI, I have to clarify that I'm looking at environmental contaminants in various media. What I am in actuality is an analytical chemist disguised as a data science / statistician. And when I was in grad school, I started posting these chemometric R codes online. And what I didn't really realize is that a lot of lawyers were going to reach out to me and ask me to help consult on different projects. And so lawyers need help from data scientists / chemists like myself in two different ways. One, you could either work for the defendant. These are large chemical manufacturing companies that are being accused of malpractice. Or two, you could work for a smaller law firm that's targeting these big chemical manufacturers for suspicion of malpractice. And usually this is determined after the accusation itself has been made. For this presentation, I'm going to be talking about a PCB study. And the funny thing about PCBs is that their manufacturing was halted way before I was around, and we're still talking about them today. The great thing about presenting before lunchtime is that the presenters before me did a phenomenal job explaining both PCBs and receptor models. So thank you to Lexus for talking about PCBs and Portland Harbor right before me. Just for those who weren't there for that presentation, a quick overview. PCBs are ubiquitous chemical contaminants that can be found anywhere in the world, even in the middle of the Arctic. What I want people to know from this presentation is that there's a specific nomenclature to naming these PCBs. They were produced as technical mixtures in the US known as air cores. The first two digits represent the number of carbons in the phenyl ring, and the last two digits represent the percent chlorine by mass. So in the example above, the 1242 represents 42% chlorine by mass, and we can see that the profile is abundant in lower chlorinated congeners, while the 1260, 60% chlorine by mass, and we can see that the profile is elevated in higher congeners. The kind of colloquial term I'm going to be using between these two is that 1242 is lighter than 1260, and 1260 is heavier than 1242. So the Portland Harbor Superfund site's been talked about quite a bit today. I'm going to give you guys just the understanding of the data that I'm playing with. I have 1,506 samples with 115 congeners. So how did I get there? The data wrangling procedure takes all publicly available sediment data online and combines them together. It also combines known technical formulation of error cores in the form of Rushnick error cores. But combining these things is not a simple feat. Different studies have different analytical parameters, and sometimes in one laboratory can measure all the congeners, but some laboratories have coelutions. So when the peaks collude together. So for example, in the above, A and B could be PCB 3 and 5. So one laboratory can measure them separately, and another laboratory actually has them colluding as one peak. So when we're combining all these publicly available data sets, we have to make sure that the coelutions align and they align with the Rushnick error cores. Missing data. One of the things I've been talking about with a lot of people at this conference, the missing values were subject to imputations. And as I remember, a person went up here and they asked a question about how did you impute these values? Well, these values were imputed on a data set by data set basis because there are different detection limits in data sets. So I wanted to make the imputation method specific to that data set that we're looking at. So like I mentioned, PCBs were never produced as one-off chemicals. They were produced primarily in the form of error core technical mixtures. So instead of looking at my data as 1,506 samples and 115 congeners, I want to start holistically looking at the profiles of the data. And we can start doing this by reducing the dimensionality down. So after we're done our imputation methodology, we can start with I call this the 50,000 feet approach method first. We can start looking at the dimension reduction through a PCA. PCA was invented by Carl Pearson in 1901. So it's a very, very, very old form of machine learning. And I like to call this a parametric machine learning algorithm because there are two things. There's parametric and non-parametric. A parametric analysis would be looking at an X by Y and looking at the magnitude differences between those. A non-parametric analysis, such as let's say a Spearman correlation, looks at the rank on X by Y and looks at in X, what's the highest one? In Y, what's the highest one? And this non-parametric technique of looking at in multivariate space, what is the closest thing to each other is kind of what t-SNE is. t-SNE is a cool new kid on the block. So if there's any bioinformaticians in the room, that's a very common technique that they would use to reduce down the dimensionality. But I know all the environmental chemists in the room are going to be saying, well, magnitudes play a very important role in environmental data, in such that high concentration samples are generally source-like samples. So we can't really just take that away from our interpretation. And in comes UMAP. This is kind of the Goldilocks zone of dimensionality reduction, where we both look at the influence of magnitudinal changes between the samples in terms of concentrations, while also looking at the profiles holistically. So now let's go through some examples of these dimensionality reduction techniques and see how they differ between each other. So the first thing you notice on this is that I'm showing the three components. So if you remember the first image I was showing you, it was spinning around. And I didn't want to have a spinning structure for each one of these techniques because that'd be very nauseating. And what else you notice is that there are colors associated with this. Just as a visual tool for communication, I ran a HCA, just with the default words method, and color the clusters based on what technical error core formulation fell into that cluster. So in this case, I'm looking at clusters that contain 1242, 1254, 1260, and one, which I'm calling the residual one, and we'll figure out why I call that later in this presentation. What you notice with this PCA, the first thing is that it kind of looks like this aux structure. Has these two different horns right there that are kind of spreading out. What you'll notice is that there isn't that much separation between the different error core formulations. If you're looking at principal component 1, you see that the largest spread is with these pink samples. And those samples have large magnitudinal differences between the congeners that are driving that difference. So the PCA is seeing that, but it's not seeing the differences between our error core profiles, which make up the majority of our data cloud. We also see that the high concentration samples aren't really clustering into one data node. In comes t-SNE. So that's that non-parametric technique that only looks at profiles and doesn't look at the influence between the magnitudes of the congeners. When we're looking at this, we can now see that we're splitting up the profiles in terms of the air core mixtures themselves. We don't really have those pink outlier samples driving the components. What I also see is this is me running at the airport. It's what it usually look like. And finally, our Goldilocks zone. So again, if you guys remember that 3D spinning image, that's the one I'm trying to showcase in 2D right now. We can see that we clearly have high concentration samples located in our data nodes. We can see that for the 1242 in the teal. We can see that we have a good splitting of all of our air core mixtures, and we don't really have clumpiness that we have for tcne. So it's a consistent gradient going in. And if we remember the structure of that dove with the crown on it, we remember seeing these small samples, the small circles in the middle of the body. What that's kind of showing you is a mixture curve where you have your source-like samples at the very extremities, and in the middle, you kind of have where they're all diverging into each other. So you can kind of read this as a meter stick, which has degrees of coordination based on where the air cores are, where the mixture samples are, and then we kind of see those crown structure again. If you look at UMAP component number 1, we can see those 3 crown structures themselves. So there are a bunch of different receptor models, and everybody seems to have their favorite one. And I don't see Lisa Rodenberg here, but she has this great analogy about a slushy machine and how that is an analogy for receptor modeling. And because plagiarism is the largest form of flattery, I'm also going to use an analogy. Who in here has ever used a streaming service such as Netflix? Okay, almost everybody had their hands up, and some people lied. So you can imagine Netflix as a very powerful receptor modeling tool. What it does is, if you look at the left, those are individuals. You can also imagine those as environmental samples, and they have movie choices, which you can imagine as PCV congeners. And based on data from all those individuals, we can factorize and create N-member profiles, profiles of movies people like, and we can determine the contribution of those profiles in each one of those individuals. And when you do a little bit of linear algebra and you multiply a contribution matrix by an N-member matrix, you get a predictive matrix. So if you've ever gone to Netflix and you've seen that this movie is a 98% match, that's actually that predictive matrix determining the prediction based on all of the fingerprints of liked movies and how much that prediction is going to match what you like. So if we look at the person with the blue sweater and the red hat, we can see that the predictive matrix is aligning really well with what his choices actually are. And that's kind of where I want to go with what N-member fits your data, because we want to be able to predict what our actual data looks like. There are a bunch of different receptor models, and I wish I had more time to go over through all of them. All of them require a different technique, and they all have their nuances. Some require you to run different coding languages such as MATLAB, R. Some of them come with a handy GUI that makes it user-friendly for a lot more other people. And there are some that do the opposite. So for example, there's an unmix, and that is what that's doing is that determining what the contribution matrix is, and you actually have known N members. So if you know you're looking at air cores, you can determine contributions in individual samples based on that. And this is the million-dollar question, is what is the optimal number of N members? How many profiles do we actually have? One of the high-level approaches of doing this really quickly is you can look at the variance predicted by the models. So again, this actual versus predicted. There becomes a point where we're predicting very well with a number of factors. So if we look at the scree plot at the very top, there's kind of an inflection point. At that inflection point, and past that inflection point, no matter how many N members we add, we're already explaining the data very well. So we have to cut off our N member at that certain point. And we can determine how well we're modeling the actual versus predicted using different metrics, cosine theta being one of them and RMSE being one of them. You can kind of just imagine that as an R squared, but a multivariate R squared. You can also look at it on a conjure by conjure basis. So instead of just predicting an entire sample profile, we might want to look at how one conjure versus the other conjure predicts. And finally, there's a thing called N-member splitting. So if we know we're looking at technical air core formulations and we run another N-member and we start splitting up, an error core mixture into two components, so an error core 1254 example into two components, we know we've gone too far with the modeling itself. And what dictates the best model? The UMAP, as we've just seen, is kind of a holistic overview of what data structures we have. So if we plot our N members into our UMAP, we want to make sure that they're hitting those data nodes where those high concentration samples are, where our technical formulations are. And so how do I usually do this on a day-to-day basis? Well, I usually create a dashboard with that UMAP, that Dove structure, and I make a big pot of coffee and I throw all my N members into there and I start playing around with it. I start looking at, okay, do 4 N members fit the data structure? What do their profiles look like? What do the cosine thetas look like? So this workflow is not a step-by-step kind of analysis. It's kind of a, you have to know all these tools are available. You have to do all these tools, and then you just got to sit there and play around with your data until it tells you something. So with Pearl and Harbor, we deduced that the NMF 6-member model was the best model that fit our data. We saw that it produced the highest match to our air core formulation, so highest match to air core formulation 1260 to 1254. It was actually able to split up 1242 and 1248, which is actually a really hard thing to do. And our UMAP even had that little diverging part. And NMF was actually able to identify those two data nodes. And again, this is that cosine theta of our N members versus our Rushnick profiles. And finally, I was able to find an N member that was representative of that crown structure. And so when we looked at those crown structures, we saw that they're elevated only in a couple of congeners. And this is really odd because air cores aren't usually just 1 or 2 congeners. So we started thinking, like, what could these be? And incidental PCBs popped right into our mind. So this is one line of evidence that potentially there are incidental PCBs located in our data cloud, and we're able to suss this out using UMAP. Another line of evidence is if I unmix the data, so if I took Rushnick formulations of all the air cores and I unmixed based on our data set, where would the residuals plot? And it seemed like all the residuals, so the non-air core PCBs, were plotting in our crown structures. When we looked at those residuals, well, they're matching our samples quite well, and they're only elevated in a couple of PCB congeners. So this is kind of producing a line of evidence that, well, these could potentially be incidental PCBs. That's it. So we are going to have a little plug here. There's a paper coming out about this topic right here. And if you want to find out more or see more presentations, just scan the QR code, it'll take you to my website, and you'll see more data science stuff.
I have one.
Yeah, go for it.
I'm not going to get up to the mic.
I can hear you.
What were the 2 congeners?
It was 206 and 209.
206 and 209.
And we looked at formulations of air cores that could potentially produce 209, 206. For example, you could look at air core 1268. But if you look at air core, the profile of air core 1268, and you were to unmix it, which I included in my data set, I tried to unmix it with it, it still produced those residuals. Because the unmixing is looking at the profile, not just of those 2 individual congeners. And if you look at 1268, it's actually got a different profile than what those samples had themselves.
Did you get that residual with all the, just in NMF or in the others as well?
That residual specifically that I was looking at would be with NMF, but more prominently you'd see with the unmix.
Okay.
That's the most prominent way you can see those residuals. And if you look at those profiles, that was just with the UMAP. I was trying to overlay what the profiles are and what the residuals are, and they look very identical. So the models aren't able to find those profiles.
Any other questions?
This is in the weeds, pretty curious, but what method did you use to seed the NMF?
What method? So that's an interesting workflow that I'm still trying to kind of play around with, because you could either seed NMF with a seed that you know of. So we do have one that we always use, for example, number 59. There's no methods why we use number 59, it's just to replicate results. But we need to